The word greatest is in here. So when you see what is the greatest distance, what would be another word you could use for that? Maximum. So we're looking for a maximum here. Agreed? Okay. So remember that x of t is a position function. And so if you wanted to, you could just start plugging numbers in as long as they're between 0 and 10 inclusive and start making some guesses. But if you remember from yesterday, there's only a certain number of candidates that really make any sense. How do you find the candidates that the ones we should even think about? Find the derivative set it equal. Like, what are we trying to find if we do that? Critical points, and then what's the other category would be endpoints. Yeah. So, I think we could start off right away and we could say that I've got two candidates, 0 and 10, and possibly some other ones. And then I'm going to just put over here distance from origin, and we'll do some comparing here in a second. But then we've got to find our other candidates, and it's what you all suggested earlier, and that is to find the derivative and set it equal to 0. So let's make sure most of this derivative is really straightforward. Well, maybe one part we have to think about a little bit. So if we're going to find x prime, what's the derivative of the first term? Negative 3t squared. That's a power rule. How about the second term's derivative? That's another power rule. What's the derivative of a constant like minus 7? 0. Awesome. And then what needs to happen, or what rule needs to be applied to the last term? Chain rule. So what do you think the derivative of 4 sine of pi t is?
4 pi cosine pi t.
Perfect. That is highly encouraging. Awesome.
Inverse tangent.
No inverse tangents on this one. Okay, so you look at that derivative, and hopefully you can get to those 3 terms in that derivative. Now we're looking for critical points, and critical points are where the derivative, in this case x prime, doesn't exist or is 0. So are there going to be any values of t for which that derivative does not exist?
Nope.
You know, you got a couple of polynomial terms and then a cosine. I think it's going to exist for all values of t, at least for this interval for sure, right? So we just want to set this equal to 0. And this is where, of course, maybe Jack was like, oh, I need to find my zeros on my calculator, right? That's exactly what you do. How many zeros did you find?
3.
There's 3 on this interval? Ooh, that's a lot. Okay, so let's see here. Let's just fill in our little table over here. At least that's what I'll do. What was the lowest critical point, lowest value? No, like when we're...
Oh, I thought you were talking about, sorry.
4.736?
So you don't count the one where it bounces?
No, sir. No.
No, because that didn't hit the axis, I don't think.
I didn't touch it.
It
Did
didn't.
it just get super close and not touch?
It doesn't
My
cost
calculator
much
started
amount.
yelling.
Sometimes you got to zoom in a little bit. Did it say no sign change?
Yeah.
Yeah, okay. So 4.736, what else?
5.63.
5.6331. Hey, one thing. Well, I'll get your question in one second. Hey, guys, just a reminder to you all, and a good maybe news bulletin for you guys. In our class, the minimum number of decimals in the end is 3 decimals. And so we'll just, like, that's an AP thing, and so we'll just kind of adopt that for the whole year. So just so you know. Forrest, your question? We will use some sign charts. We will not be using sign charts when we're finding extrema on an interval because the endpoints come into play. When we get into like the relatively high and relatively low points, a sign chart is a great tool to kind of visualize what's happening. We will definitely use those. Just not when we're finding absolute extrema.
Oh, okay.
We can globalize that sort of argument, and we can use some intervals, and we can kind of turn it into that. But really, all we have to do is just compare the outputs and decide what's the highest.
I've never done that before. I need to...
Okay, if you're finding extrema on an interval, like on a closed interval, I'm referring to this guy right here. We're doing an extrema. We're trying to find max and min on a closed interval. You really have to test out your candidates. It's not enough for me to say, oh, let me put it like this. Well, I'll give you an illustration in a second. What's the third one? You said there were 3?
6.026.
6.026. Okay, so Forrest and everybody, when we're talking about absolute extrema, we're talking about the highest in our world, right? It's like the highest it could possibly be. So if we make a sign chart, what we're really doing is we're saying, hey, where does the derivative go from positive to negative or negative to positive, right? That's what we're looking for. That makes sense? So we've got to be really careful with this, because if our test for like the absolute highest of all just involved the derivative changing from positive to negative, we could take that a little bit too far. So for example, like if we all look down this way, you all see the hills on the southern skyline? We could walk down there, right? So if we walk down there, and I want you to get this, if we walk down there, wouldn't our slope as we're walking up be positive? And we'd get to the top, somewhere over there by Mountain Vista or wherever, and then we'd start to walk down. So then our slope would be negative, right? So if our slope went from positive to negative, does that mean that we reached the highest point on Earth? No. Does it mean that we reached a relatively high point?
Yeah.
Sure. It was
But
higher
you're
than the
like-
surrounding area.
But you're in the interval, so you don't have to.
Depends on what your interval is, right?
Yeah.
What if there's multiple ups and downs? What about the endpoints? So what if this, we're going to find out in a second.
Maybe use a third.
No.
No, second. Sorry.
No, it's okay. That's okay. It's a good question. It's a good way to kind of parse between absolute and relatively high or low
Because I'm
points.
kind of confused. Like we only did like sign charts before. Like all we do is sign charts.
I-
Last year the class.
You either didn't do the full picture,
No.
or I'm not totally understanding. I think you
'cause-
probably just didn't find these. It would be my
No,
guess.
it's like we don't do like comparisons.
You really have to, like, I want to kind of keep moving here because we could probably spend our entire time discussing this, and we can't afford to do that, unfortunately. We can continue to kind of converse about that. And this actually, the finish of this might actually be really helpful. Let's find out the results here, okay? So I've got my 5 candidates. Have you guys done any plugging in? Okay, so we're looking for distance from origin. So when I plug in a 0, I get -7, and so I'm going to say that the distance is just a 7 for a point of comparison, right? Because -7, whether I'm to the left or right of the origin, doesn't really matter. I'm 7 away from the origin. What happened when you plugged in the next one, 4.736? What was the output there?
69.161.
Okay, so that clearly is much larger than 7 as a distance. So that would be a leading candidate right now, right? How about the next one, 5.631?
64.45.
4.5 what?
1.
1, okay. You guys agree with that? 64.451, all right. What about the 6.026?
65.0075 or 76.
Okay, so I'll go with that. Is that good? I mean, Logan was right, of course, but I just rounded off to 3 decimals. How about the last one, the 10?
207.
So, yeah, -207 point something. What was the something?
Exactly.
Oh, it was exactly?
Yeah.
Okay, fair enough. And so, of course, as a distance, we'd say that that's just 207. And actually, Forrest, I would say this is an excellent example of what I was just talking about. Because I would say here, I bet x prime went from positive to negative. I would guess. So it'd be a relative max. I am guessing that here in red, I'm guessing that's where x prime went from negative to positive, so a relative minimum, right? And then here, I'm guessing we go back to a relative max because x prime probably went from positive to negative. But none of those 3 is actually where the maximum distance happens. It's actually the endpoint, and at the endpoint, I bet you there is no sign change from negative to positive or positive to negative. So a sign chart would not have revealed that. Right? We would have just like stopped at the 10 and picked the wrong one using a sign chart. Using a table to compare, we're able to find the one that's the biggest or the smallest, whatever we're looking for.
Okay.
Does that make sense?
Yeah.
Okay. We'll keep processing. There's a lot more to talk about, and if more questions come up, let me know. Okay. Anybody else? Good questions. Thank you for asking. Like, I hope you take that the right way. I think these are all things we all could hear, and sometimes I see AB students all the time that some question like that gets asked, and we talk about it, and the AB student who's a veteran and probably made a 5 last year is like, whoa, I never thought about it that way. I think I understand it better. So thank you. Seriously. Okay. Anybody? Anything come up for anybody on that one? Okay, awesome. So then let's move ahead, and let's take a look at the mean value theorem for veterans, this was the speed trap last year. And for non-veterans or for folks that just wanted to join and be like a beneficial member of the class, I'm going to do it again in my red and orange ABs. It's fun. Did you guys have fun with it?
It's awesome.
I had really enjoyed it. Every year I wonder if it'll be the last year because someone's going to do something really stupid, but so far it's gone well. We'll see. We shall see. Okay, so whether you just remember this from before, maybe you watched the intro video, there are two conditions for which the mean value theorem needs in order for it to be true. You guys remember what those two conditions are?
Continuous and differentiable.
Got to be a continuous and differentiable function or graph. Got to be that. And so when you look at a question like number 1, it says if f of x equals that whole big piecewise thing, determine whether the mean value theorem can be applied to f on the closed interval 0 to 2 pi. If it can be applied, go ahead and use it to find a value or values. And if it can't, explain why not. So the can you use it or can you not, it's rooted in those two conditions, right? So you need to test, is this function continuous on the interval we care about? And if it is it also differentiable on the interval that we care about? And if you can figure those things out, you'll start to be able to form an answer. So how you feeling with the whole continuity and showing good work? I can't decide if this is one we should do together or if you should just try on your own. What do you think? You let me know. So yeah, like Jack and Aiden, I don't know how much you guys know about continuity. Like
It's
we haven't
continuous.
we haven't dug too deep into that. You'll see. So you guys just want to try it? You're welcome to it, or I'd be happy to do it with you, whatever. Okay, I'll give you a few minutes to at least explore and decide if continuity is in play here. So guys, I'm going to just kind of work quietly back here real quick. Feel free to ignore the screen for a few minutes here, or you can look too if you want.
I think I need my notes from last year because I kind
Sure.
of forgot.
Well, we'll get you up to speed here.
Okay.
So the first thing we're going to check is continuity. And here's how you do it. In order for a function to be continuous at a point, the limit as x approaches, in this case, pi is where the function rule changes, right?
Yeah.
So as x approaches pi from the left, has to equal the limit as x approaches pi from the right. Does that make sense?
Yeah.
And then those two things have to equal the actual y value of the function at that same x value.
Okay, I see.
So if that statement proves to be true, once we get the specific, numerical analysis in there, if that's true, then we have a continuous function.
Okay.
If that's false, if any part of that is false, not continuous.
Yeah, my problem is just like sometimes I don't understand that question, like what it's asking for.
And that's what we need to work on, right? Because, we want you to be able to, take what you're seeing and interpret it correctly without, and this one's tough, right? Because I didn't say anything about what the conditions were, and so you need to be able to, start into that continuity piece. I don't know.
Mm-hmm.
Like I think a lot of it will naturally happen, but if things come up for you, like that one, maybe we could work on something specific too.
Yeah, I got some like problems. Like I think it's like different language. It's kind of hard for me. To
No, I understand. I understand.
Yeah. But so
What country are you from?
China.
From China. Okay.
Yeah.
Yeah. So I've had a couple of Chinese students over the years, Korean, just with some language
I
things.
actually just met a Korean guy.
Sean, Minsu,
I forgot. He's a senior and he plays tennis.
violin. Yeah, that's Sean.
Okay.
Yep. His real name is Minsu.
Yeah, he's very nice.
Yeah, real nice guy. He'd be someone, I'm sure there's still a language barrier there because I don't know how similar Korean and Chinese are. I'm sure they're pretty different, but I think you guys would have a lot in common.
Maybe.
Just culturally and like working into the school here and everything.
Yeah. I don't know. Like I was in the public school like last year, and I was like changing like everything is like so different.
You'll find that a lot of people care about you here. I can't speak. I can't speak for all public schools. I'm sure there's good and bad, right? But you'll be cared for here for sure.
Okay, thank you.
Yeah, you bet. Hey, did you guys have something like that for your continuity?
We did something
Like this would be where you'd start, right? Maybe you've got the specific rule for f of x in there or something like that, but you need a right-hand limit, you need a left-hand limit, and the value of the function. Meg, you guys good with this?
Yeah, we have it.
It makes the continuity piece makes sense? So, okay, so you help me out here. So as you approach pi from the left, what'd you get?
Pi plus 2.
Pi plus 2.
Pi plus 2. Yeah, it's like 1 over pi times pi squared plus 2, right? So, sure, pi plus 2 makes sense. And then is that maybe equal to, we approach pi from the right. You can directly substitute here, sine of 2 pi plus, it's the same, isn't it? It's 0 plus pi plus 2. And of course, the value of the function is contained within the bottom piece. And so, sure enough, all three of those elements are equal. Therefore, this is a continuous function. And maybe the MVT can be applied. But what else do we have to check? Differentiable. Okay, so we did this. Now we're going to switch over and see if it really is a differentiable function. And of course, differentiable means there's no sharp points and no vertical asymptotes, things like that, right? It's continuous, or it's differentiable is what we're looking for here. So I am going to start off by finding my first derivative. So f prime would equal, it would be 2 over pi times x if x is less than pi. And oh my gosh, what do we have to use for the first term?
Chain rule.
Chain rule again. Yep, so it'd be 2 cosine of 2x. And of course, wait a minute, I know the derivative of 2 is 0, but what's the derivative of pi?
0.
Why?
Because it's constant.
That's also a constant, right? It's a fancy constant, but it's just a constant. Okay, so that's if x is greater than pi. Technically, we're supposed to leave the or equal to off that part because we don't know if this is differentiable yet. And if we put or equal to, we're basically saying that we have a derivative there. We just don't know yet, right? Anyways, minor detail there, perhaps. So, to check the differentiability, we need to use limits again. We'll go limit as x approaches pi from the left. Of the left piece is 2 over pi times x, and maybe that's equal to the limit as we approach pi from the right of the other piece, and that's 2 cosine of 2x. So does this end up being true? Yes. So 2 equals 2. Wow, okay. So that means this is a differentiable function, which means that the MVT does apply. And so we could actually use the MVT, which the hypothesis for it is right here. We can actually use the MVT to maybe find these places where the instantaneous slope, aka the derivative, equals the average slope. So we've shown the two conditions are met here. Does that make sense? Continuity, differentiability. Okay. So then let's go ahead and find this. Have you guys found what f of 2 pi minus f of 0 would be? Let's see here. F of 2 pi, that would be 5 plus 2 minus 2 pi. Sure. Yeah, it's pi over 2 pi, isn't it? I'm doing a little work in my head. I don't know how far you guys got with that, but I'll switch colors here. So if you find that f of 2 pi minus f of 0 over 2 pi, I think we end up with pi over 2 pi, which is 1/2. I agree with you there. And then this wants us to find where f prime is equal to 1/2. So I'll just put 1/2 is equal to f prime of c. I'd say this is maybe where the calculator probably comes into play. How many times are we going to have to actually do this in order to actually solve this equation? How many pieces are there? 2. So we're going to set 1/2 equal to 2 over pi x. We'll set 1/2 equal to 2 cosine 2x. Does that make sense?
Why is there's 2 of them?
Because it's piecewise. It's a continuous and differentiable piecewise. So if all I did, so I'm going to kind of go a little bit backwards here. If I work in this little red box, if all I did was write 1/2 is equal to 2 over pi x, and this is obviously a relatively easy equation to solve for you guys. What does this end up being? Pi over 4 is equal to x. If that's all I did, I'm ignoring the possibility that the other piece, the 2 cosine of 2x, might also fulfill this equation as well, right? So not only do I have to do that, I need to also set 1/2 equal to 2 cosine of 2x. And maybe that's the calculator part, right? So you're going to get 1/4 equals cosine 2x, not a nice unit circle number. And so we end up with, I don't know, did you guys do this and get some answers?
0.659.
Just one answer? At least on the interval that we care about? 0.659? Okay. I'll believe you. I don't have these answers memorized. So it looks like there's possibly, assuming that there's no other answers from that trig equation, looks like we got 2 answers, right? Pi over 4 and 0.659. Those would be the 2 places where the instantaneous slope and the average slope are the same. Questions, thoughts? This is by far the most involved of all the things we're going to look at today as far as all the details and things like that. Question, yes, sir?
Wouldn't there only be one because 0.659 is less than pi? And the second equation is almost half of pi.
Is that, I'm relying on you guys. Like I said, I don't have these answers memorized. Is that even, so 0.659, does that even apply to the piece that we're looking at?
I don't think so.
So the piece we're looking at there is bigger than pi, and sure, 0.659 is not bigger than pi, so that's not even a part of that piece, is it? Okay, yeah, I agree. So I hope you guys are comfortable with this. Like when we do examples, I'm not going to be like the final answer man unless I have to be. This is more of a collaborative effort on your part. And so Aiden's thought of like, whoa, wait a minute, that doesn't even fit. I'm good with that. Are you guys, that make sense? Yeah, so let's be critical thinkers. I'll usually be a critical thinker, but yeah, that one doesn't even fit. Pi over 4 certainly fits. That's less than pi, so that fits the piece that we're concerned about. Yeah. Okay. Any other questions, comments, thoughts? Okay, cool. Well, then let's skip ahead a little bit. We are going to, I think we'll skip the number 2 for the moment and do the number 3. Yes, let's do number 3. Yes, check this one out. It says mean value theorem does not apply to that function f of x on the interval -2 to 5, and we are interested in why. What reason would we have for saying that the mean value theorem doesn't apply to that function on that interval? What do you think? You just go in order. F of 0 is not defined. That's a pretty easy test, right? What is f of 0? 0. So I would say f of 0 is defined. So that's not it. What about f of x is not continuous? Think about what causes discontinuities.
It's continuous.
Yeah, until, I mean, yeah, because there's no.
What are the different types of discontinuities? There's the whole, which usually is a rational function. The jump thing, yeah, we all get the hand motion down. Yeah, and where do jumps usually come into play? Piecewise, and that's not piecewise. What's the other discontinuity? And there's no asymptotes there, right? There's no, it's not rational. So I think we have a continuous function. I agree. Logan, you're right. You said it right away. It is continuous. Okay. F prime of -1 does not exist. That's a pretty easy thing to figure out, right? So if you find f prime real quick, f prime would be 2/3 x to the -1/3. Would it be okay to plug a -1 in for x? So the negative on the exponent means what? Flip it down. Is it okay to divide by -1 to the 1/3? Sure it is. What does 1/3 power mean? Cube root. And can you do the cube root of a negative? Yes, you can. So I would say f prime of -1. I guess it would be negative 2/3. It definitely does exist. Okay. F of x is not defined for positive or for negative numbers, I should say. This is getting at roots, right?
No, yeah, it's
Because it's what kind of a root?
It's a cube root.
Cube root. And can you do a cube root of negative numbers?
Yes.
Sure, you can.
The numbers are always positive anyway because x is squared.
Well, it depends on the order you're doing it. You could do the cube root first, right?
And I,
Well, yeah, I
But you always do like a
and then do
square.
the cube.
Yeah.
wait, does it matter?
You can do it the other order.
Sure it does. If it was 3 halves, I'm saying in general the order matters. In this case, squaring it and then cube rooting it or cube rooting it and then squaring it doesn't matter. But if it was 3 halves, now all of a sudden it'd make a huge difference, right?
Which one are you supposed to do first?
Doesn't matter.
It shouldn't matter.
Oh, okay. I always do this.
I usually try to make the number smaller than larger instead of even bigger than smaller. I do what you do, I think. Yeah. Okay, so that leaves us with E. And I think you can see that E is true because if you did try to plug a 0 in for that F prime that I have up there, do you see how you'd get a 0 in the denominator?
And you can't have that.
And you can't have that.
That's
That's right.
fine.
Good. Yes, therefore.
Very true, very true. So good, so good. Okay, let's at least take a peek at that one example with the wind chill. The wind chill, yeah.
It would just be 0 to any.
0 to any power.
Okay, so let's see here. Let's at least get this started. We just don't have time to spare to like lose 3 minutes just for the fun of it. So you get this wind chill situation. It gives you this lovely equation expressing the wind chill in terms of velocity. And then it asks us to find the average rate of change of W. And this phrase sometimes will really be a struggle for folks. When you're asked to find the average rate of change of something, like in this case W, what do? What are we finding? What would be another way to put it? Average rate of change? No, actually the derivative would be the instantaneous rate of change at a point. We're talking about the average rate of change over this interval.
The slope of the line between the 2 points.
The average slope, right? This goes back to the old delta y over delta x thing, or in this case it'd be delta w over delta v, right? So for this, find the average rate of change, I would say w of 60 minus w of 5 over 60 minus 5. That's average rate of change. It's the old school slope you learned way back in like 8th grade or 7th grade or whatever the case might be.
Kindergarten.
Or Naden's case when he was 7. That's what Nick seems to think. I don't know. Okay.
That's what Mr. Blank says.
Yeah, you got to be careful. He'll get after you for sure.
He told me.
So W of 60 minus W of 5. Let's finish here. Use your calculators. Let's figure out what this average rate of change is. And then when I see y'all on Monday, we'll finish off. And hopefully, again, that'll be a good connector. And then I think by the end of Monday, we should be on track, or at least sort of close. We shall see. It's going to work out almost perfect. Average rate of change, W of 60 minus W of 5 over 60 minus 5. Anybody have it? Santi almost has it.
Hurry.
Stop. You got it. The fate of the class depends.
I don't know. You guys are like ripping on him 40 minutes ago, and now he's your hero.
Exactly.
I'm not missing that.
That's like really confusing.
That's the way it has to be.
Mr. Anderson, you only see the good side of Santi.
Okay.
That was enough to show his bad side.
Alright.
Anybody have an answer?
Aiden does.
I think so.
Aiden, we'll throw it out there and we'll see if anybody agrees with you.
Wait, negative 0.25 or 0.254.
Negative 0.254.
I believe it.
That's what I got.
You got the same thing? The two youngest people in the class, I believe. Right? They agree.
Are they old sophomores?
Aiden, tell them how old you are.
Huh?
Aiden, tell her how old you are.
How old are you?
I'm 14.
Holy!
I skipped fifth grade.
Feel good about yourself.
I was 14 my whole summer.
I was.
Have a lovely weekend, you guys. Please sign up for AP Classroom and See you on Monday.
What about is the 80 puzzle also something we have to sign up with?
Yeah, for sure.
Wait, so you're a sophomore.
Yeah, if you